Okay, Physics H. Here we go. I got a new little recording set up here for school that Mr. Roboto made for me. Nice little phone stand. We're going to start getting into some actual physics problems here. So just to recap really quick, we do have some basic equations that we can use here. And I'm going to be giving you an equation sheet once we get done with this worksheet 3 here. All right? Actually, probably halfway through worksheet 4. But for now, here's what we have. We have average velocity is displacement over time. That shouldn't go over there. Sorry about that. Average velocity equals displacement over time. All right. And then we also have, if we multiply both sides by time here, right, we have displacement equals average velocity times time. Now, we talked about in class that average velocity, you can literally just take the average of the final and the initial velocities, v final plus v initial over 2, the literal average of the two. And then we also have acceleration equals change in velocity over time. All right. And then we could take that and rearrange it and solve for the final velocity. So change of velocity is v final minus v initial over t. So if we solve for v final, we multiply both sides by t and then bring the v initial over here. So we'd end up with v final equals v initial plus a t. So we have 1, 2, 3, 4, and then 5 equations. V average equals delta x over t. And that's all we have right now. That's all we know. And this one's really important. This is y equals mx plus b for a velocity versus time graph, which is what we're being asked to do on this worksheet here. So a poorly tuned car accelerates from rest to a speed of 28 meters per second in 20 seconds. Make a well-labeled diagram of the situation. All right. So a poorly tuned car. When I first got this problem, it was a poorly tuned Geo Metro, which, you know, even when I first got the problem, no one knew what a Geo Metro was. It was Geo was a car company. It was a spin-off of Chevy, and they basically rebranded Toyota cars. So a Geo Metro, I think, was a Toyota Corolla, possibly, or even the little smaller one, the Celica, maybe, which I don't think exists anymore, the Celica. All right, v final equals 28 meters per second. So start off at rest, and by the end, it's moving pretty fast. So clearly, this object is accelerating. So I like to sometimes draw a big arrow showing the acceleration of the object. And the time it takes, the time interval here is 20 seconds. So that's all I'm looking for the diagram, kind of what's happening here, right? Make a well-labeled graphical representation of this situation. All right, so this is your graph. Just means make a graph. So let's see, 5, 10, 15, 20. Okay, or I could do 10, 5, 10, 15, 20. I guess I'll do that. 5, 10, 15, 20. And that's seconds. Velocity up to 28. So, you know, if I want to use the whole scale, I could figure that out, or I could go up to 30. 5, 10, 15, 20, 25, 30. I think that's what I'll do. 5, 10, 15, 20, 25, 30. 20, 25, 30. So at 20 meters per second, I'm at 28 meters per second. And then my line is a constant increase in velocity. Now, maybe I should have gone up by 4s. So 4, 8, 12. 24, 28, maybe that would have made more sense, but this will be good enough. So what is the average acceleration of the car? So average acceleration, it just means acceleration. For our purposes, there is no difference between the average acceleration and the acceleration. So acceleration equals change in velocity over time. So we're gaining plus 28 meters per second in 20 seconds. So 28 divided by 20, that's like 1.4, I suppose. So 2.8 divided by 2 is 1.4 meters per second, or meters per second squared. And it'd be positive because the slope of this line is positive. So you can use the equation, but the equation really is just the equation for the slope of this line. How far does it travel? Okay, so I could do a couple things here. I could do average velocity times time, right? Or I could find the area under the curve. I'm going to do them both and show you that it's the same thing. So the area under the curve here, right? Delta x is the area under this curve, which would be 1/2 base times height, which is 1/2 of the base, which is 20 seconds, times the height, which is 28 meters per second. The seconds cancel. So 1/2 of 20 is 10. 10 times 28 is 280. So delta x equals 280 meters. That's the area under the curve calculation. Now, the other thing I just said was we could do average velocity times time. So let's just check our results here. So delta x equals average velocity times time. Well, let's see, what's the average velocity? It's the average of the final and the initial. So it's final is 28 plus our initial, which is 0. The initial velocity is 0 over 2. So that's our average velocity times the time of 20 seconds. And look, it's the same thing. It's a half of 20, because it's half of 28 times 20. Well, it's half of 20 times 20. It's the same thing. 280 meters. Cool, it works. Physics works. All right? So that's that first one. The next one. Now, these are real physics problems now, right? But I do want you to follow the instructions here. Draw the graph. Try to answer the question using the graph before you try to answer it using the equations here. All right? Here we go. T equals 0. Car has a speed of 30 meters per second. After 6 seconds, its speed is 15 meters per second. Draw a well-labeled diagram. All right, so it's another car, but in this situation, it's starting off, V initial equals 30 meters per second. It's starting off with a big velocity, and then some time later, its speed has been reduced to 15 meters per second. So it's lost half its velocity in a time of 6 seconds. Now, which direction is the acceleration in? Well, it turns out, since it's slowing down, the acceleration is actually negative because it's opposite the direction of its motion. So when an object, this is a little side note, slows down, the acceleration is opposite the velocity. The direction of the acceleration is opposite the direction of the velocity. Or the acceleration vector, which is this arrow, is opposite the velocity vector, which are those two arrows. So it's a negative acceleration in this case, which makes sense because, let's see, 5, 10, 20, 5, 10, 15, 20, 25, 30. 30 meters per second. 5s make sense here. 5, 10, 15, 20, 25, 30. And we're getting in 6 seconds. So I'll just do 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 seconds. So it's 6 seconds, it's 15. Once at 0, it's 30. Nice straight line down to 6 seconds, sort of straight. Maybe I should use a ruler, but that'll be good for now. All right. Part C, list given quantities and quantities to find as you determine the car's average acceleration during this time interval. So what does that mean? List given quantities and quantities to find. As the car's acceleration. Well, acceleration equals change in velocity over time, which is V final minus V initial over T. Or it's the slope of the line. So I've already listed out everything I need here, right? V initial, V final, and time. So it's 15 meters per second minus 30 meters per second over 6 seconds. 15 minus 30, that's negative 15, so it's losing 15 meters per second in 6 seconds. And 15 divided by 30, or 15 divided by 6, oh, I guess that's like 2.5. All right, negative 2.5 meters per second squared for an acceleration. So I don't really need to do anything there. It's just changing velocity over time. And we're just going to then move on with these questions, right? So we just kind of keep going through here. Well-labeled diagram, so that's again the drawing. Graphical representation, how's the velocity changing over time? This one is an interesting one because you don't know the final velocity. You know the displacement and the acceleration. So you might have to do some things to find the final velocity right before it hits the ground. Anytime you drop something, the final velocity is always the velocity the instant before it hits the ground. So if you drop something, right, it's 30-meter distance. V initial, if you drop it, is 0. V final is the speed right before it hits the ground. Its acceleration is down, and it's telling us, so delta x is going to be 30. Acceleration is going to be 10 meters per second per second. It's accelerating down. So later on, we'll talk about how maybe we should make these negative. It's accelerating in the negative direction, but we won't worry about that right now. We'll just pretend that's the positive direction. Almost be like turning this sideways. You know, it's accelerating in the positive direction at a rate of 10 meters per second each second. So I don't know how to set up the scale, right? I don't know how long it's going to take to hit the ground. I don't know the final velocity. I know the distance. So we're going to have to figure out what to do here. All right. So we'll see what you can do with this one. See if anybody can kind of get a start here. I'll give you a hint. We know delta x equals average velocity times time. We know a equals change in velocity over time. All right. Might be able to do something with that. We know V initial is 0, right? So delta x is V final plus V initial over 2. That's average velocity times time. A is V final minus V initial over t. All right, we know V initial is 0. So maybe we can figure out some algebra here to be able to kind of put these two together. I don't know. We'll see. See what you can do with that. That's a fun one. All right. I'll check you guys later. Be good.